So far, we have only analysed systems subject to initial displacements and velocities. This is an important step to understanding the pure dynamic properties of a system, but it is not entirely realistic, as most structures are subject to an externally applied force. There are a great variety of externally applied forces, some of which have precise analytical descriptions, and others are more arbitrary. For any of these external forces to be of interest in dynamic analysis, they must vary with time, and crucially, they must vary at a frequency that is significant for the structure. As a rough approximation, the load becomes dynamically significant as the frequency of the applied loading approaches the natural frequency of the structure. Response to force vibrations is a complex subject, and in this course we will restrict ourselves to harmonic forcing functions due to their analytical simplicity. A typical harmonic forcing function for PT can be described as either P0 sine capital omega t or P0 cosine capital omega t. In this equation, P0 is the amplitude and omega is what we call the forcing frequency. Using our familiar representation of force undamped systems, such as this one, where we have a rigid mass and a spring, a single degree of freedom response, ut, and this time we can specify our forcing function as one of the two given above. In this case, we're going to work with the sine forcing function. Using this setup then, the equation of motion can be written as the inertia force plus the stiffness, this time set equal to P0 sine capital omega t. Even though, in this case, we have a forcing function, we still cannot solve this system without specifying the initial conditions. As before, the initial conditions are given by u0 and u.0 at t equal to 0. This time, however, the equation of motion to be solved is an inhomogeneous ordinary differential equation. As such, we need to evaluate two components. Firstly, the particular integral, and secondly, the complementary function. The particular integral can be done and evaluated by proposing a function that is the same form as the forcing function. So we denote the particular integral as u subscript p of t, and we're saying that this time it takes the form of d, a constant d, times by sine capital omega t. This then has the following derivatives. The first derivative with respect to time is omega, capital Omega d, cosine capital Omega t, and the acceleration is then minus capital Omega squared d sine Omega t. If we then substitute 3, 4 and 5 into equation 2, we end up with minus m times by capital Omega squared d sine capital Omega t plus k times by d sine capital Omega t plus p naught, equal to p naught sine Omega t. As we've got signs on both sides of this equation, these all divide through. So we end up with minus m over k times by capital Omega squared times d plus d equal to p naught over k. As we've noted before, the natural frequency, which this time we will call omega n to distinguish it from any other omegas, is equal to k over m square rooted. So equation 7 now becomes 1 minus 1 over omega n squared times by capital Omega squared, all times by d, equal to p naught over k. Rearranging and solving for d, we then have d is equal to p naught over k times by 1 over 1 minus the square of the forcing frequency divided by the square of the natural frequency. The particular integral is then defined as up of t, substituting in now our value for d, times by sine omega t. The complementary function is, in this case, the solution to the homogeneous version of the equation of motion shown in equation 2. That is the solution to this problem, which we should recognize as our free, undamped vibration problem. We have previously shown then that the solution to this is given by ut, but this time we're going to put a subscript c on it to denote the complementary function as being equal to a cosine times by the natural frequency of t plus b sine omega n t. The complete solution to the problem then is given by ut equal to the complementary function plus the particular integral which gives us A cosine omega nt plus B sine omega n t plus P naught over K times by 1 over 1 minus capital omega squared over omega n squared times by sine omega t. The only thing left now to do is to apply our initial conditions. So taking derivatives of equation 12, we then have minus omega n A sine omega nt plus omega n B cosine omega nt plus capital Omega P naught over K times by 1 over 1 minus capital Omega over omega n both squared, again times by sine omega t. Applying the initial conditions, u naught and u dot naught at time equal to 0, we can firstly say that u naught is equal to A, and secondly u dot of naught is equal to omega n times by B plus capital Omega times by P naught over K times by 1 over 1 minus capital Omega over omega n squared. So solving for B in this equation gives us the initial velocity divided by the natural frequency from which we subtract the forcing frequency times by the amplitude of the forcing function divided by the natural frequency times by the stiffness, all multiplied by this ratio 1 minus capital Omega squared over the natural frequency squared. We can now then specify the complete solution to our force vibration problem as ut being equal to u naught cosine omega nt plus our initial velocity divided by the natural frequency minus capital Omega P naught over omega n times by K times by 1 minus omega squared over the natural frequency squared times by sine omega n times by t, plus then our particular integral part P naught over K times by 1 over 1 minus capital Omega squared over the natural frequency squared times by sine capital Omega t. The first part of this equation we will call the transient component, and the second part we will call the steady state component. Plotting this equation out, you can see then we get our steady state response shown by this dashed line, and our transient component oscillating around the steady state response. In this case, we decided to normalize by the natural period, where the natural period, which we denote by Tn, is equal to 2 pi over the natural frequency.